At this stage, we're going to start looking at analytical solutions for transient problems where you have to worry about time-dependent behavior. So, in our initial discussion of analytical transients, we assumed that the BO number was small, less than 0.1, and we could neglect the temperature gradients. And this gave us lumped capacitance. However, in many cases, the BO number is greater than 1, and then we can't use lumped capacitance anymore. So we look at this simplified version of the heat equation. What we've done here is eliminated heat generation. We're ignoring heat generation. And then we've divided through by rho c to give us this equation. Now, we have a time-dependent term here, so we need an initial condition, and we also have an x-coordinate, so we need two boundary conditions. So our initial condition is just at time 0, the whole thing is at a constant temperature, T initial. Then our boundary condition is on all the boundaries, K dt dx is equal to H delta T. So it's just conduction heat flux equals convection heat flux. And we can solve this either analytically or numerical. So we're going to start with the analytical solution, and we'll look at numerical solutions a little later. We begin this process with dimensional analysis. We look at Buckingham pi to figure out how many dimensionless terms we need, and then we can use the method of repeating variables to figure out our dimensionless terms. So what we can do is reduce the complexity of this problem. So we define our dimensionless terms, and now we have our boundary conditions, right? Our initial dimensionless temperature, and then our dimensionless conduction and convection terms. So this allows us to reduce the problem in the boundary conditions to only 4 variables. We have theta star, x star, BO number, and Fourier number. So what this means is, as long as you can come up with expressions for those 4 variables, all the solutions will look roughly the same. So we solve this by separation of variables, just like we did for the 2D case. And the process is very similar. So we look at this plane wall. We have identical boundary conditions on both sides. H and T infinity are the same on both sides. We make x equals 0 the middle of the wall. And then so we have half thickness on either side. This allows us to use symmetry. We assume that there's a symmetric condition at the center, which allows us to only look at one side, and we have a adiabatic condition in the middle, which means that the gradient at x equals 0 is 0. So as with 2D conduction, the solution here is an infinite series. We have this cosine function in the x direction where it peaks in the middle and it's lower near the edges. And we have exponential in time, which is much like lump capacitance behavior, so we kind of expected that. Now, unless the Fourier number is very small, well, in this case, very small means less than 0.2, we can approximate this equation only by the first term in the infinite series. So we're only looking at n equals 1. Now, the way to think about this is, at very small times, Fourier number smaller than 0.2, the temperature change hasn't yet reached the middle of the object. So it doesn't quite look like that cosine shape yet. And in order to recover that shape, you need to have these additional terms to make it look like it's the right shape. When the time is bigger, the temperature change reaches the center of the object. And the shape of this temperature profile reaches a quasi-steady cosine shape. So for longer times, then the first term is sufficient because it adequately captures that behavior. Now, if the Fourier number is small, less than 0.2, it means the heat transfer hasn't reached the center of the object yet. So we can actually use the semi-infinite solid approximation for Module 1 as a reliable model for the area near the surface, where we can look at the heat transfer right near the surface. We also, again, have solutions for cylinders and spheres. They're tabulated in textbooks. You can see the equations are similar. However, the cylinder case has a Bessel function, and the sphere uses a sine function instead of a cosine function. So, again, in many cases, this one-term approximation is sufficient. We can get the values of C1 and Zeta 1 in tables from various textbooks in different cases based on the BO number. So in this case, the process for solving these systems is to identify the geometry, a cylinder, sphere, or a plane wall from the previous slide, and then select the appropriate equation for the dimensionless temperature. Then you calculate the BO number just like you would for lump capacitance. And once you have the BO number, you go to the table and you look up the value for C1 and zeta 1. And then you either calculate the temperature or the Fourier number and then the time, depending on what the problem is asking. I want to note here that as the BO number approaches infinity, for the plane, zeta 1 becomes pi over 2, zeta cylinder becomes 2.405 from the Bessel function, and zeta for the sphere becomes pi from the sine. BO number is infinity means H is infinity, which represents a constant surface temperature boundary condition. So if you're looking at a temperature, a heat transfer problem, and it gives you a constant temperature boundary, you can assume that H is infinity, and you can use the bottom line on the table like this. Now, these are very useful for estimating the solution to some simplified problems. However, just like the solutions for 2D conduction, it's very limited because the system has to be pretty simplified. So again, for engineering calculations, we typically rely on numerical methods.